Okay, good morning, everyone. Thank you for coming to our tutorial. My name is Shireen Sohrabi. I'm one of the presenters for this tutorial titled Finding Multiple Plans for Classical Planning Problems. My co-presenters are Michael Katz, Junkyu Lee from IBM Research, and David Speck from University of Basel, Switzerland. Go. Okay. All right, so what we're going to cover in this tutorial is based on this set of papers that is shown here. I also want to mention that all of our slides are available on our webpage that's linkable from the ICAPS website, tutorial site. Okay, so here's an outline of our tutorial. We're going to start with introduction and motivation. And we're going to talk about planning problems. In particular, we're going to talk about diverse planning. That's then we're going to switch, and Michael was going to cover top K planning and top quality planning. And then we're going to move on to planning methods. And Michael will continue with 4-bit iterative. Then we are going to switch to David, Junkyu, who's going to talk about K-star. And then we're going to switch to David, who's going to talk about SimK. And we are also going to have a hands-on session. Also, if you go to our website, all the materials regarding the hands-on session is available for you to download. So I know this is an ICAPS audience, but we're just going to level set here on some of these terminologies. So what is AI planning? So AI planning is a task of finding a procedural course of actions for a declarative described system to reach its goals while optimizing the overall performance measures. Typically, a planning problem includes initial state, the goal state, and a set of possible actions. The objective here is to find a plan, which is a sequence of actions that will guarantee you to go from the initial state to a goal state. In many realistic settings, the space of possibilities and the space of search is large, so optimization is important and it's key. And in many settings, you actually want to find top quality plan, or you care about the quality of the plans that you find. And in some settings, you care about finding a set of plans, whether that set is diverse, top quality, or top K, which is the topic of this tutorial. Now, AI planning is everywhere, whether it's IT, cybersecurity, logistics, dialogue. And in many of these settings, I want to point out that you don't have your typical initial state goal outlined for you ahead of time. And it may be really hard to know exactly how planning problems are actually used here. Nevertheless, AI planning is used, and the key there is transformations or compilation steps that are required in order to enable use of planning in many of these settings. Also, AI planning is everywhere, and in regard to where we are today, we are living in a very interesting time where AI planning is mentioned by many well-known researchers, and there's a lot of traffic on Twitter and social media where it does mention planning in whatever sense that may be. And there are lots of different papers now that mention planning, and some of them published in NeurIPS with very high number of citations. I want to sort of point out to this picture, which is from a survey that was recently published that sort of outlines the space of planning abilities within the large language models. But I want to point out that that's not the scope of this tutorial. I just want to sort of mention that planning is everywhere, but we're not going to be covering any of these for the scope of this tutorial. All right, so many of the work that we're going to be presenting today are motivated by applications. So a lot of different applications that we've been involved with, dating back to 2013, where we saw a need for a new planning problem that did not exist before, which would capture finding a set of top quality or top K plans. And some examples are here. For example, hypothesis exploration for malware detection or cybersecurity was one that we noticed, or moving on to scenario planning. For a couple of years, we worked on that project and dialogue, and more recently, the last two items, which I'm going to cover very briefly, is the second to last is called Lemming, which is an interactive plan selection. We have it in a demo in AAAI, and also we had a demo last year at ICAPS. And also for the problem of sequencing APIs for the purpose of dialogue, and that's a demo that we have for this ICAPS. So just a little bit touching upon an application or one of the recent applications that we worked on that does require us to find a set of plans. And this is this Lemming problem. So one of the very important and challenging problems when it comes to finding more than one plan is the task of how do you show these many plans to the user? You need to really have a good visualization tool that will enable them to see the huge search space that we now have narrowed down to a set of plans, but in a systematic way. And in this problem, we actually looked at how do you use disjunctive action landmarks to enable users to have different views, in particular selection view or build view. So you go from this left image, which has this huge sort of tree-shaped structure, which basically every path through this would be a plan, to something that maybe is smaller. They will have a better ability to visualize, and the goal here is that the user is actually interested in one of these plans. So how do we guide them to get to that one plan that they're interested in? So that was one of the projects that we worked on. And one of the more recent one is this task of sequencing APIs. So now these days, a lot of these APIs are available on the web. They have open API spec associated with them that you can take and potentially use to compile down to PDL or your favorite planning formalism. And here the task is you have this builder, which is used to compose different APIs in some sort of a control flow. And we are providing guidance for the user to help them figure out what are the potential associations between these actions or APIs in this case, and give them suggestions. So for example, they have picked already a download the content of a file. And as you notice, this is the UI. This is, by the way, we are going to be demoing this in the demo session. And this is a screenshot of an actual product that IBM uses. And you see pluses on the left and right. So if the user selects on the plus on the left, then this window sort of comes up on the UI, which will give them 4 suggestions. And the behind the scene AI planning is used. We find a set of plans, and in particular for this problem, we came to a realization that we actually need a new formalism that does not exist before, a new planning problem. And we call that partially ordered top quality plans, because there are some orders between actions that people do not care about. For example, this could be auxiliary or bookkeeping actions, but there are some orders between actions that people really do care about. And so we need some sort of a middle ground between fully unordered top quality to not ignoring all the orders. And this was partially ordered planning, top quality planning. And once they click on the plus, they sort of continue. This is an iterative approach. Now they have 2 items on the right, the right top. And then again, planning problem is used in the back end with the pluses, and they get solutions. In real world settings, you're also constrained by what the product or customers will entail on you. And in this particular case, we had a time bound of 5 seconds. So we had to put bounds on time and also the number of plans that we generate, and then do all kind of post-processing on top of it to get to where we are today. let me pause there. If there is any questions, we are happy to take questions along the way. Okay, so now if you were to think about a framework for all of the work that we're going to talk about today, whether that's top quality, top K, or diverse, here's one. You start with data, and this is your domain knowledge in whatever form that they may be. And then you have to address the domain engineering or modeling challenge, which is basically any gap between figuring out that you are going to use a planning, you have a planning problem and you want to use a planner to actually come up with a PDDL that you can then give to the planner. So you have your planning model, then you give it to the planner. And here the planner could be any of the planners that we're going to cover today in this tutorial. And then you get plans, which means you get more than one plan. Sometimes you get lots of plans, thousands of plans. And then you have to post-process all of these plans, whether that's a visualization or in any other way that basically requires you to show all of these plans and capture them in a systematic way and present them to the user, which is the end person who's going to be using this tool. And then you get feedback. And sometimes based on the feedback, you may need to adjust your cost, you may need to adjust your model, and sort of iteratively go through this process. So that's basically sort of the framework that captures all of the work that we have here. Yes, Mark.
Is one of the things that you're adjusting the number, what constitutes a difference for the user? Because I'm generating commercial plans, right? Actually, this, for example, some of these differences, it's like, okay, you gave me 2 plans and you could provide, the 49th and 50th actions have been converted. I don't care. So the kind of thing that you're, no, it's maybe I'm getting ahead of the tutorials, but if you're talking about, diverse plans or meaningful differences, but even if you're doing something like top K, right? It's like you gave me 10 plans, all of which differ in ways that I, as a user, find utterly trivial. Right? That's the question I'm asking about: is how do you account for different definitions of what's trivial in terms of differences between plans?
So we do have, I would say it's really dependent on the application and what they're going to see. One of the implementations that we had was a simple thumbs up, thumbs down on the results that they see. I don't think that will capture all of the likes and dislikes, but it sort of maybe to some extent captures some of the properties that the user will have in their mind. But I would say it's really dependent on the particular implementation of the sort of the application and how you want to get the feedback.
Yeah,
yeah. So it's talking about it would be during the development.
Correct. So that's what she mentioned, that the fish was even better, right? Different formula, because they have seen that formula didn't
the formula is PDL, it's in the express as well.
No, the planning problem.
The planning.
Which we're going to cover right now. That's a good segue to what are the different planning problems that we're going to capture. But let me just quickly cover some of these. So why multiple plans? There may be more than one reason, and here I'm just outlining at least 3. So we don't live in a perfect world, right? Things are not always captured perfectly, whether that's your knowledge, that means your domain. And sometimes your knowledge is actually unknown, or maybe it's known, but it's really hard to capture. You may have missing preconditions, missing effects, and we do see that, just to give you an example, going back to the API sequencing, the input for us is the API, the specifications of the APIs that are in a format of, open API specs. And the people who wrote those open API specs do not necessarily know that we are at the end going to translate them into preconditions, effects, etc. So they may not really capture everything that they had in mind. They have to only talk about the minimum requirements in order for the Open API to be valid. So many of these things are actually missing, and they end up coming to us, and we capture them in our knowledge. The second reason is that things are underspecified. So you have users, but they may not necessarily represent everything or all the constraints to us ahead of time. There could be orderings between actions that are important, and there could be orderings between actions that are actually not as important. So just giving examples. So let's say in OpenStack, you have to make products, and there may be priorities over these products. Think about Amazon, like there are some customers that will get them faster or not. But in logistics, for example, the drive action, the ordering between the drive action may not be as important as making sure things happen. And furthermore, we do have a lot of bookkeeping actions or auxiliary actions that came from the transformations that we do in the pre-processing to come to the PDDL model. So all of those can essentially be ignored. So we have a mix of orderings that are important, not important, and preferences that may not necessarily be all captured. And finally, replanning or plan failure, which, by the way, was one of the main reasons for diverse planning. When diverse planning came up, that was one of the motivations for it. We live in an environment where we actually need to execute these plans. So if something fails, you have a backup. So we have a number of different class of problems. And here I outline some of them, and it really depends on the application that you have in mind, and figuring out which of these would suit you better. So the goal of the tutorial is to go through all of these, both a little bit more formally, and also how to actually compute these. But just to give you a preview, if you want K best plans, your best bet is to use a top K planning. And if K is smaller than the number of optimal plans, basically all of these plans are optimal. But if K is larger than your size of optimal plan, you get some near optimal plans in the end. Now, if you want top quality plans, so you want to have you don't know what K is, but you have a bound on the quality of the plans. So your best bet there is top quality planning. And then in that case, you have to see whether you care about the order between actions or you don't care about the order between actions. And that would be unordered top quality planning and partially ordered top quality planning. And in the last case here, diverse planning. So you want to find a set of diverse plans, and that could be basically comparing plans pairwise, a distance between the plans that you have in the set. We'll talk about that in a second. But even in the case of diverse planning, you may care about quality. So you want to have a potentially both quality and diversity as metrics that you want to either bound or optimize. So that essentially gives us a hierarchy of different computational problems under the umbrella of diverse planning that I'm going to cover in a few minutes. So now let's go a little bit on more formally on these planning problems that I just mentioned. But before that, let's again level set on what's the classical planning model. So a classical planning model consists of 6 tuples, 6 elements in a tuple. You have a finite and discrete state space S. You have a known initial state S0. You have a goal state. You have a set of actions. A subset of them are applicable actions. You have a deterministic transition function that will take you from a state and an action that's an applicable action to a new state S prime. And you also have non-negative action costs that are associated with the action and the state. Now, in order you need to, what is the solution? The solution is a sequence of applicable actions that maps you from the initial state S0 to the goal state. So now, in order to compactly represent this planning model, we use languages, and the most famous and commonly used one is the strips. Strip planning task consists of 5 elements. First one is finite set of atoms or Boolean variables. You have set of operators that are represented by add, delete, and preconditions, and all of the most subset of atoms. You have operator cost, non-negative operator cost. You have your initial states, which is a subset of atoms. And you have your goal description that also is a subset of atoms. So what's the plan? Is a sequence of applicable actions that map the initial state I to a consistent, that's I into a state that's consistent with your goal. Now, strip planning task will determine what's the model, planning model here. So here the state S0 are collections of atoms from our F. The initial state S0 is I. The goal state is basically a subset of S. So S is a superset of your goal. You have your actions that have, that are in operators O, such as the preconditions are met. So these are applicable actions. And you also determine what the next state is by getting S, adding all the add effects, and then deleting the delete effect. And here, the cost of the actions are only determined by the action and not the state. So the solution of the planning model would be all the plans for your planning task. So now we have many different computational problems for classical planning, starting with cost optimality. So you want to actually minimize the sum of the operator costs. You care about the cost of these plans. You care about optimality. In some cases, you don't necessarily care about that. You care about the cheaper plans better. So you find a plan, cheaper plans are better, but you just find any plan, satisfies them, right? Agile, you care about time, so quicker the better. Top K, as I mentioned, you find K plans, such as no cheaper plans exist in your set of K plans. And top quality planning, so you find all plans up to a certain cost. So you don't have a K, but you have a bound on the cost of the plans. And diverse planning, which is a variety of different problems that aim both at the dimension of diversity as well as quality. So there is history with diverse planning. So we were not the first to come up with the notion of diverse planning, unlike the other problems that we talk about, including top K or top quality. But in regard to the history of diverse planning, there are many different papers that date back to 2011, 2012, and so on, that do talk about what it means to find diverse set of plans. In the first one, you care about finding a set of plans, and the size of these plans are K. So there was no mention of diversity or pairwise distance between them. But you just find a set of plans, and the size of that set is K. In the later work, you bring in the notion of diversity, which is a comparison between actions and looking at the distance between the actions, whether, and I'll mention that in the next slide, whether plans are considered as set of actions or as a set of states. And you want to find those distances between them to be at least of a distance d. So d is given to you. And then later on, you actually also care about the cost. So now you also have a bound on the quality of the plans that are generated by your diverse planners. And there could be many others here that did mention diverse planning in the literature. Now, as I mentioned before, there is not something called the diversity metric, and then there's a history about what does it mean to find distances between two different plans. In the earlier work, there's a notion of stability metric, which is comparing plans based on the actions of these plans. And then later work in state metric came that basically looks at plans as a set of states and compares them based on the number of differences between the two plans as a set of states. And we also have landmark-based diversity metric, which looks at the systematic difference between the disjunctive action landmarks, between them. And then also notion of uniqueness that came in 2014 that measures where the two plans are permutations of each other, and one plan is a partial plan of the other. So there are many different diversity metrics that exist in the literature. Now, when it comes to quality metric, there was one that is on the top. That's from the literature. And we introduced this one in 2020. So I don't know whether that's it's still considered new, but this is the one that we introduced. And there are multiple differences between these diversity quality metrics in regard to the two plans. In the top one, you actually the quality is relative to a known set of plans, P. So you have, it's not an absolute, it's a relative number. And on the bottom, this is an absolute where C star is the cost of the best plan that you found so far. But you also need to look into the max cost of the P and your P prime. So anyway, there are also multiple quality metrics that exist. So now, given your diversity metrics and your quality metrics, what are the space of possible computational problems for a diverse planning problem? And that gives us this hierarchy of different planning problems under the notion of diversity. So similar to how we had satisficing, optimality, unbounded. Let me see if the pointer works. We have satisficing diverse planning. We have optimal diverse planning, and all combinations of bounded. Some of them also optimal with some dimensions. So we have here optimal diverse, optimally the diversity diverse planning, or sometimes they are bounded on one dimension. So this is bounded on quality and also bounded on diversity. So this gives us all of these computational problems under diversity, and the arrows here are set inclusion. So for example, in the Pareto optimal one, which is the top, if you found a solution that's a solution to this problem, because we have this edge, basically means it's also a solution to this and this problem. Now, what do we have in the literature? So we introduce all of these planning problems, but that does not mean that all of them will actually have a planner associated with them. These three that I highlight do have planners associated with them that exist in the literature now. Optimal quality K is basically our favorite top K planning problem. So it maps to a normal top K planning. Satisficing diversity, this one is, any planner just finds that cares about diversity. In particular, for example, LPG is a famous diverse planner that belongs to this category. And then you have bounded diversity diverse planning, which I believe this one would be, it's one of the other planners that exist out there. Now, what we introduced in 2020 are highlighted in green. So we introduced a number of different planners and approaches that address one of these. And one thing I just want to highlight before I pass it to Michael is that many of the diverse planning approaches that existed in the literature took into account these diversity metrics or the quality metrics within their computation. So they actually changed the planner to take those metrics into account while they're computing the plans, whereas the planners that we introduced are doing it in the post-processing. So we find a set of plans, and then with some different approaches, we actually post-process these plans to take into account all of the diversity metrics or the quality metrics that we have in mind. So it's not hard-coded into any of our planners. All right, so with that, I pass it to Michael.
Yes. Okay, so I would like to emphasize again that the moment you have any questions, just stop me and ask them, okay? So let's dive into the top quality plane.
as Shirin mentioned, we are talking about classical planning formalism. So pi is the planning task, and we denote by P of pi the set of all plans for pi. It could be, in some cases, it could be an infinite set. Still, it's the set of all plans for pi. So then cost optimal planning can be viewed as a task of finding one plan out of that set, which minimizes the cost, right? So the top K planning, this definition existed since 2012, 13, 14, sorry. In one way or another, this particular definition was written in 2018. I think they're essentially the same, but there is a slight difference. So given a planning task and a natural number, you want to find a set of plans such that if the set is smaller than K, that means that is must be all the plans for the planning problem. Okay? And otherwise, there should be no plan outside of the set that is smaller cost than the plan inside the set. So far, so good? Okay, so there are a few issues with this definition. Basically, says, okay, so we need the parameter K. Usually this is application dependent. Most application were using rule of thumb to set 1,000 plans, more or less, right? And then, if you found enough plans, great. If you didn't find enough plans, you increase your K, and so on, right? So the main problem was that the set of plans that you get is really, in many cases, many of them are indistinguishable from the application perspective, right? So like Mark mentioned before, you might have two plans that differ in the order of two actions that are really not important from the actual application perspective. So Shirin mentioned the example of sequencing APIs. Like the order between APIs is important, but the order between actions that achieve the preconditions of APIs, right? That feed the information inside the input of the API call, really don't care in which order they will be performed, right? So so then one of the that was the motivation for actually introducing the notion of top quality and quotient top quality planning problems. So starting with top quality, given a planning task and the cost bound, the task is to find all plans under that cost bound, right? It simplifies greatly the definition, right? You don't need to consider the size of the task. The problem here is that set of plans can still be infinite, right? We'll get back to it later, but in principle, that can happen, right? So I will make a side note that in practice you can actually impose two bounds, both Q and K, right? And then you will get your favorite pick, right? But that's getting ahead of myself, right? So so moving on to quotient top quality planning, that is the problem that should take care of the issue of having indistinguishability from the application perspective. So if you have equivalence relation defined on a set of plans that will tell you these two plans are equivalent, then you can take this equivalence relation and plug it into your definition, right? And say, okay, now we have the quality bound, right? We have the equivalence relation, and we want to find a set of plans such that every equivalence class will be represented, right? So basically, you don't need equivalent plans, but you need at least one plan representation from every equivalence class, right? So that means that the union of all equivalent classes of the plans in the set are the top quality planning solution, right? So then you can plug in your favorite equivalence relation, and our favorite equivalence relation for a long time was this. So this equivalence relation says, okay, you have two plans. They are equivalent if their multisets are equivalent, right? So if they have the same actions, exactly the same counts of ground actions, possibly in different orders, right? But this completely ignores the orders between them, right? So just saying, okay, we have two plans, we treat them as multisets of actions. If they are the same, then these two plans are the same. Questions? No. Great. Then, as Shirin mentioned, we come to a realization that, okay, so in some applications that actually doesn't give you sufficient information, right? So it doesn't give you sufficient plans, because sometimes you actually have a few actions that you care about the orders between them. For instance, again, taking you back to API sequencing, if you have two APIs, right, that should be applied before the third one that you need to give a recommendation for, then yes.
I didn't mean to interrupt, but you have a question.
Go ahead.
Okay, when you're talking about caring about and ordering out some subset of the actions, like presuming that all the things developed, care about those actions because of some of these unexpressed user preferences?
Yes, exactly, right? Because some of the user preferences are not part of the model, right? So then you need to consider these two predecessors of these two APIs, these two predecessor APIs of that API that you care about, right? And consider them in any order, because you get more information from each, right?
Yeah, but the point for the formal problem is, if it's a matter of correctness, then I put it in the model. It's a matter of user just kind of wants it that way. It's not in the model. Then you end up with something that you should get.
But sometimes you cannot put it in the model.
Oh, absolutely.
Right.
I'm not arguing you should be in the model.
Right.
Distinguish.
Yes.
Yeah.
So from the model perspective, these are indistinguishable. Well, they are distinguishable as plans. These are different plans, right? So we want to be able to capture both of these plans, right? But we don't want to capture plans that are different only in other actions that are just maintenance actions, right? So then our equivalence relation changes, and then in addition to having these plans be equivalent as multisets, we actually also require that when their sequence, like they're treated as sequence of actions restricted to the set X, they will be the same sequences. Okay. Okay, let's go on. So there was another computational problem that was mentioning is so-called subset top quality planning problem, which is actually not defined as in terms of equivalence relation, because the relation that defines this. Okay, so in this planning problem, the intention was to find plans such that if you have two plans that are, one of them is a superset of the other one, you actually don't care about the superset, right? It's sufficient for you, right, to find the one that is short, right? It's already includes all the information. It might be good for some applications, it might be bad for other applications, but there definitely exist applications that require this, right? But here it's not an equivalence relation anymore, right? So the relation between these two plans is a dominance relation. So so then the corresponding computational problem would be then, okay, so given a planning task and a natural number Q, find a set of plans such that, first of all the plans must be under the cost bound, and second, for all the plans that are not in the found set, there is a plan in the found set that dominates them. Okay, so the relation would be this, right? And we will remember this relation because we'll use it later on. So there was another formalism that David introduced recently, and here this comes to overcome. Okay, so these two actually came to overcome some issues. The first issue that this overcomes, and like I mentioned before, the plan sets can be infinite, right? So even unordered top quality plan planning solutions can be infinite plans, infinite sets of plans. Sorry. Here, for subset of quality planning problems, actually the solutions are finite, right? If you find the minimal such set, right? If you, or at least there exists a finite set of plans P that is a solution for a top subset of quality planning problem. The second issue was that maybe you don't want to reduce all the dominated plans like that, but you want to skip the plans that have loops, right? So David introduced the loopless top quality planning, David and the colleagues, right? Sorry. And in that, well, top K planning, but top quality planning defines the same way. Yeah. Loop is a loop as a sequence of state changes, right? So it visits the same state more than once. Yes. Well, plans are so here the subset is a subset of multisets, right? So action multisets. So the two plans are comparable in terms of they're using the same actions. So A, B, and C, D as plans would be incomparable. They would need to be part of the solution, but A, B, C, D wouldn't. No, both of them for every plan. Oh, I see what you mean here. No, but you must have all of them. Right. Yeah. So yeah. So for loopless top quality planning, basically you can define the set of all loopless plans, and then you can define this analogously to the top K or top quality planning problem, right? Over the set of loopless plans. But I don't remember whether this is the next slide. Yeah. So right. So the loopless top I've shown loopless top K. This is the loopless top quality planning problem. So basically, as I said, the same replacing the P pi with PLL pi, which is the set of all loopless plans. Right. So in principle, and this is this is fresh from the press. This is a paper that was accepted to this ICAPS. We can unify now all definitions under this dominant top quality planning problem, right? Because the amount of definitions that we had so far was unmanageable, and it's getting worse and worse, right? So so we can unify it under the same dominant top quality planning problem. So given a planning task pi and a natural number q, again, you want to find a set of plans P such that first, obviously, all the plans on P must be under the cost bound. Second, if you don't have a plan in P, that means that it's dominated by a plan that is in P, right? And to answer your question, the other, like the AB will be here because it's not dominated by anyone, and CD will be here because it's not dominated by anyone, but ABCD will not, right? Or shouldn't, right? Right. And the third condition is something that we didn't have in the previous definitions, but it was actually in all implementations. We were always using, we were always finding the minimal such set, right, under the subset relation, right? So, so why not put in it as part of the definition now? Right? Any questions? Yes? No? Okay, so now, okay, let's see how it actually unifies everything. So for empty relation, we get the top quality plan, right? For RU, which is the unordered relation, we get the unordered top quality planning problem. Works for every plan not there, it must be there, right? So, so for R subset, we get the subset of quality planning problem. That was just copy paste from the previous definition, basically. Right? So and for loopless, we didn't have a relation, but now we do. This relation is not as nicely mathematically written as the previous ones, but it basically says, okay, so two plans are in RLL if and only if the first one is loopless, and B, the second one traverses some at least one of the states of the first plan more than once, right? It might be a completely different plan in other respects, right? But it does make a loop over one of the states of the first plan. Okay, so under this loopless relation, we actually have the loopless top quality planning problem. Okay, I'll pause again for questions. Good on time. We were expecting more questions, so think of some. Okay, so then we come to the most interesting problems, the questions. Sorry, right? So given these computational problems, now we need to understand how hard they actually are, right? How to solve these problems, right? And how to check whether the set of plans is actually a solution. Okay, so I will talk next about the first one. And yes, there are some results. Thank you, David. But there are very, very few results, and we need more. And then we will all talk about the second question, how to solve, and we will focus on that question for the rest of the presentation, for the rest of the tutorial, and for checking or certifying the sets as solutions for the computational problems, I invite you to come to my talk tomorrow. And I will just tell that I will have surprisingly small amount of time, so I will give you surprisingly small amount of details during the presentation then. But I would invite you to come to the paper, to go to the paper and read it. So let's go. So what's the computational complexity of finding multiple plans? So analogously to bounded classical planning, we will define, or you will define, a computational decision problems for top K planning, which is basically given a planning task and a length bound L and the number of plans K, are there at least K plans for pi of length at most L? And not surprisingly, at least p-space complete. Surprisingly, it is p-space complete, right? So next, for polynomially bounded top-K plan existence. The result is that it becomes PP hard, right? And it seems to be like from what we see from practical from practice, we see that it seems to be very much harder than the ordinary classical cost optimal planning. And these are all the results that we have. Okay, so I invite you to give us more. Okay, so this concludes the planning definitions, the planning problem definitions, and now we are moving on to methods. I will start with forbit iterative, and then I will switch to GenQ, and then to David. Okay, so give me one sec. So the fun part, how do we solve it? So in 2018, we introduced this idea of forbit iterative, which is a very simple idea of use the classical planner to find one solution, then possibly extend that solution somehow without search by applying symmetries or reordering actions, and then transform the planning problem that you had as an input to a new planning problem that forbids exactly that set of plans, and repeat. Find the one plan for the new problem, extend that set, and so on. So at some point, you either found enough plans, or you proved unsolvable, or you got stuck solving the problem. Now, there are several transformations that were introduced. So the first one was to forbid one single plan. Then we could use it for top-K or top-quality planning problem. Then there was a transformation that forbids multiple plans as a set of plans. Then there was a transformation that forbids multiple plans as a graph, basically capturing more than that set of plans, but possible interactions that will switch from one plan to another plan, right? So this is a graph of paths of states that these plans traverse. And then there was a transformation that forbids a plan and all its reorderings, all its possible reorderings. And then you can use it for another top quality planning. And then there was a transformation that forbid plans and all plans whose action multisets are supersets of the action multisets of that plan, action multiset of that plan. And then you could use it for a subset of quality planning. You could use multisets or sets, doesn't matter, right? There are two different transformations, one for that and one for that. So basically, these transformations would count the number of times that each action was applied. So then there was a transformation that forbids all plans that correspond to a given prefix, and that was used in robotics. Then there was a transformation that we introduced this year, or there is a transformation that we introduced this year that correspond to the loopless relation that I have shown you before, and that forbids a plan and all plans that loop through at least one of the states of the given plan. So I will not introduce all of these, but I will introduce one. I will take you through the simplest out of these transformations. It's not that complicated. I will show you exactly what it does. So the dark part, the black parts are the original task, and the blue parts are the additions. Okay, so basically, given a planning task and a plan, what you create is a new planning task where the set of variables is extended by these n+2 binary variables, right? Where the initial state is then extended with the initial state of v overline would be 1. The initial value of the v overline would be 1, and of the v overline 0 will be 1, and all the rest will be 0. Okay, so as you can imagine, we will trace that plan execution. We'll see whether it's still executing the plan, and the goal of the planning task is extended by adding another goal variable. The overline should be 0, so it should change from 1 to 0, basically, right? So the idea here is that we are tracing the execution of this plan, and the moment that we moved away from the plan, we are allowing to reach the goal, right? Okay, so as long as we are tracing the execution of the plan, we are not allowing to reach the goal. The moment that we indicate that the move from that trace was made, we are allowing to change the goal. So the actions, therefore, we have multiple representatives for every action in the original planning task. So and let me take you through those representatives. So the first one is the simplest case is for each actions that are not part of the input pi, right? For the input plan, these actions are not on the plan, right? And we add one effect that it just reaches the goal value of that v overline variable, basically discarding this plan from consideration, right? So if we apply this action, we have moved away from. We know that we have moved away from executing that plan. Then the next one is actually action on the plan in the right order. So basically, OI at the moment after OI minus 1 was applied. How do we trace it? We are using these variables, and we are setting this one first to 1, and then every time that we apply an action, like if we applied O0, O1, then we switch that one to right. So if we are still not right, so if we are still tracing the plan, and the value of the corresponding index -1, right, is 1, right? So we are moving the token 1 through that through this array of variables from v0 to v1, right? So if that's the case, then OI has additional effects of shifting the 1 from I-1 to I. Okay. So basically, we are saying, okay, we indicated that this is OI that was applied after O1 to OI-1. Okay. Now, action on a plan that is not in the right order will break the execution, and we will discard the plan from consideration. What it means for an action not to be in the right order, it means that its corresponding OI is 0, I-1, right? So then we add the v overline 0 to the effect and discard the plan from consideration, allowing to reach a goal. And the last one, if we already discarded the plan from consideration and we execute another action from that plan, then it's just you just continue, right? Because we already discarded, right? So then the precondition is already v over line 0, and we don't need to add anything to that. Okay, so that was the transformation. I will just flesh out the transformation, the transformation for loopless top quality planning that I mentioned, and we had 4 action types or representative types in the previous one. Here we have all these according to the different colors, right? This is not nice. I will not present it here. But basically, this works, right? So if you are using this transformation within the forbidden iterative framework that is yet to be implemented, by the way, sorry, then you can solve loopless top quality plan. I have to say a disclaimer that these transformations increase the size of the planning problem, sometimes significantly, right? In our papers, we measure that and we show how much does it increase. In practice, it means that if your K is relatively small, and I guess we'll see some results, right? I don't remember. If your K is relatively small, like in 5 stents, then forbidden iterative works great because it can reuse the latest and best cost optimal planners, right? But if your K is large, you might use different approaches. One might want to use different approaches, and I invite you, Q here to tell you about the first one of those. And we are way ahead of schedule, right? So we'll start this. Right? Yeah, maybe, yes, maybe you have any questions that were not asked before. General, yeah.
So about the transformation, you have a theoretical result about how much it increases the polynomial size, like
So let me first say that this is a presentation without conditional effects, right? You can do this with conditional effects in a way more compact way because basically these are the same actions, right? They have different preconditions, but you can encode this as different conditional effects instead. It will not increase as much, right? It's still a linear thing. I don't remember. It's in the paper definitely. It does not grow exponentially, right? It's still, but the problem is that it's a it's a linear increase in the representation size, right? Which is translates to an the state transition system is exponentially larger than the representation size. Right?
about the next one.
This one is, yeah, in practice, I don't know what happens here because it's not implemented yet, but it's the same, right? So we have a constant number of types. So it's a larger constant. Constant, yeah. You should be careful with constants, definitely. Yes.
Example you do show represented as something like in the
This one, yeah.
I'm just wondering about the formalism for expressing these transformations. How do you write them down? I'm not saying it's a hard problem. I'm saying.
So
what I'm looking at here, like you say, you have a set of binary variables.
Right. So this is implemented in FDR or SAS+, right? Right, which is grounded representation, right? Yeah. So on the ground level, you can write it down, right? These are just a list of actions. On the lifted level, we don't know how to do that.
That's exactly.
No, that we don't know how to do that on the lifted level. I think it might be. I mean, the problem is that the input is the plan on the ground level, right?
But that's why I asked the question about how you express the transformations, right? So I can take potential and well, potential. I haven't done either. Could express these transformations in a lifted representation that then applied to ground plans. Right?
So I think that you can do it with like static predicates that correspond to the ground plan actions. Basically, you would need to introduce some static predicates probably. And then you put it in the initial state, basically, right? And like you define which, like, what is the ground plan by the static predicate values in the initial state.
Yeah.
I'm guessing here because I mean.
Until maybe the other this is done, it's all this.
Yeah, so the thing is that we really don't need to do that because I mean we really don't want to transform it back and forth, right? Because when we are implemented in a planner, we first transform this we ground the PDDL to a ground representation to SAS plus or FDR, right? And then we use that grounded representation, right? We solve the planning problem for the grounded representation. We find the plan, the grounded plan. Then we transform it into a grounded representation that can be used again by the planner, right? We don't need to go up to the PDDL, lifted PDDL, and then ground it again. Yes.
Lifting the grounded plan, so this lifted plan would somehow be like an equivalence relation of symmetric plans.
So you want to like introduce multiple like lift in the plan in what sense? Like multiple that correspond to multiple ground plans?
Yeah.
Yeah.
That's an idea. Seems like you would go out the symmetric plans anyway.
I'm not sure that okay, so the symmetry would not be the symmetries that we capture that actually go beyond object symmetries, right? So it may be symmetries between different actions, right? Then it's not clear how to do that. No, I understand what you're trying to do, and that's a great idea. But I mean, you might capture some of the symmetries, like object symmetries, and use them. Yeah. Okay. Thank you. Thank you. You might be able to switch the entropy.
Let's see. So hello. So the plan was to talk about K-Star Planner for 20 minutes, maybe 15 minutes plus some question. But seeing that we have some enough time, I may go a little bit slow, or you could ask more questions. So this part will be by 10 a.m. and then after coffee break, we will continue 1.5 hours. So let me talk about K-Star Planner. So currently, I think K-Star Planner is the state-of-the-art planner for finding multiple plans. There are only 3 planners for this one. So, so overviewing K-Star Planner. So what it does is that it implements K-Star search algorithm in fast download. And then basically K-Star alternates A-star and Epstein's algorithm. So I'm going to assume that we know A-star algorithm and less about Epstein's algorithm. So I'm mostly talking about Epstein's algorithm today. And then while we were implementing K-Star Planner, we made several modifications to the original K-Star search algorithm, as well as Epstein's algorithm to improve the performance and to use as a PDDL planner. So, yeah. Okay. So one nice thing about this K-Star Planner is that it's very easy to integrate existing techniques for A-star search. So essentially, if you have some way to improve A-star, then it will work for K-star anyway. That's because at very high level, what K-star does is that it simply stores all edges, that's called sidetrack edges later on, generated during A-star search, and then somehow it gives you all the passes using Epstein's algorithm. So it has ability to generate all the suboptimal paths, given that you store all edges somehow. Therefore, you know, the modification that made on A-star would really transparently work on K-star. So therefore, if you just add, let's say, symmetry pruning technique on top of K-star, then it's gonna be the best for top K. And then if you add partial order reduction on top of K-star, then it works well for another top quality. And then if you also add another kind of pruning technique, modified partial order reduction, then it also works for another kind of, you know, formulation for the multi-plan problems. So I'm not going to talk about each details. If you're interested in, then you could go over each papers, or you know, you could ask questions later on, yeah, about this. So this is the basic outline of the K-star search. Three parts. There are three parts. So the first one is to build the necessary data structure for running Epstein's algorithm during A-star search. So it essentially alternating A-star and then Epstein algorithm. And then it has to switch between A-star search and then Epstein algorithm. And then once you reach that Epstein part, then you decode solution passes and so on. So if it's a top K planning problem, and then if you were able to decode, let's say, enough plans, then you are done. But if you're not enough, then you have to go back to A-star and then explore more search space to collect more sidetrack edges, and you have to explore nodes to construct suboptimal paths and so on. That's the very high level overview. So essentially, it's switching A-star and then Epstein, A-star, Epstein until you find solution, or you know that you cannot really solve the problem because there are not enough paths exist in the problem, something like that. Therefore, this first switching can only happen after finishing the A-star. So which means that you can start Epstein only after finding the first optimal path. So, are there any questions at this point? Okay. There will be examples here, but let me just give more conceptual overview on this K-best enumeration with Epstein's algorithm. So regarding the complexity, so finding K-best paths in an explicit graph, here it's not implicit graph, but explicit graph means that you expanded everything where you have n nodes and m edges, then Epstein's algorithm returns paths with loops. And it assumes that you have a single source and a single terminal node and costa or non-negative. Then the complexity results is going to be m plus n log n plus k. And if you look at the complexity for the Dijkstra for finding only one plan, one optimal path, the difference is going to be O of k, constant. It's not constant, but people are, by looking at this, it's kind of constant time overhead one per plan. So if you are finding million plans, then the overhead is going to be big O of 1 million, that amount, which is very nice. And then this running time as well as the space complexity is known to be the best so far for finding K-best enumerations. When it comes to the case where you cannot have loops, then Yen's algorithm is known to be the best, but complexity results looks a little bit different here, right? So n comes in front of m n plus log n and so on. And then later on, Professor Epstein also wrote an article about general idea about K-best enumeration for solving discrete optimization problem. And then I think these three ingredients are very nice to highlight. So to solve these types of problem well, then you have to have dynamic programming kind of things. Problem decomposition by dynamic programming is one piece. And then you should have a solution space partitioning. That's going to giving you kind of search space in the end so that you can explore your solutions very nicely. And then you have to have fast selection method for finding k-best items among many, many items. So if this step is slow, then overall things will slow down. So today we will focus on Epstein's algorithm and show the ideas by examples. So dynamic programming or this kind of representation for path is a kind of very nice in Epstein's algorithm. So any path in a graph can be represented by sidetracked edges. The definition of the sidetracked edges are the edges that are not on the shortest path. So in case of k-star search, you actually obtain this shortest path tree by maintaining the search tree with the A-star that maintains the best path to each node. And in case of Epstein's algorithm, it were just solving explicit graph. So you run Dijkstra once to have shortest path tree, and then from there you know the graph so that you can have sidetrack edges. So in this example, so on the left, this is the input graph with 5 nodes, and S0 is the source, and then S4 is terminal, and so on. After running Dijkstra's algorithm, this is the shortest path tree, and then optimal path is going to be S0, S1, and S4 with cost 4. And then the remaining kind of edges denoted by dotted arcs are all sidetrack edges. By convention, this is following the incoming edge convention shown in k-star paper. If you just happen to read Epstein's paper, it's reversed. He's defining with respect to the outgoing edges. It's same, but it's quite easier to see it in this way when it comes to A-star search, because you keep generating search space in a forward way when you run A-star algorithm. And this is another example on a path. So this path is one suboptimal path with cost 5. So you see that 2, 3 overall 5, and then you can represent this suboptimal path with the shortest path tree over here, and then one sidetrack edge. So you deviate from here with using this sidetrack edge, and then from here you just follow the path in the shortest path tree. That's going to give you a path. And here's another example, post 3137. And for representing this path, so you can have 2 deviations relative to this shortest path tree. So you deviate from S4 by using this sidetrack edge. And then you deviate once more from here using another sidetrack edge. And then the remaining kind of edges will follow the edges in the shortest path tree here. So that's how you can represent any path using this Epstein's path representation. So is there any questions at this point? So I'm just kind of repeating the definitions. Okay. Multiple shortest paths to the same node. So for them, it doesn't matter. So it's based on kind of sorting things, and then you are talking about, I guess, ties. You can choose. You can choose anyone as a shortest path, and then the remaining will store in a data structure later on, and you still enumerate passes according to its path cost. So ordering can be different when they are all in tie, but it doesn't break the whole ordering based on the cost. Does it make sense?
But one of the shortest paths could be in the sidetrack.
No. So okay. So I think you are talking about this can be many, right? Depending on. Yeah, you just fix one as a reference, and then the remaining things will become sidetrack edges.
One more question also about this. You mentioned the terminal is 40.
Yes, this is.
And the shortest path is like
not directly to the terminal, but it's the shortest path to all of the nodes from, so it doesn't have the.
So this one from here, here, yeah. Okay, thank you. So understanding this means that you understand Epstein's algorithm in the end, because what Epstein's algorithm does is that you trace back these sidetrack edges from here to here in a kind of organized way. And in summary, so dynamic programming essentially executes over the optimal substructures, right? And then this is in the end the same. So there's an optimal substructure in this kind of k-shortest path finding problem by Epstein's algorithm here. And then there are two types of decisions. So you can have the deviation decisions, selecting the sidetrack edges, can be made along the shortest path tree from the terminal to the source that we saw in the example. And then those deviation decisions can be ordered. And then any subsequent suboptimal paths obtained by adding additional sidetrack edges from the previous one is going to be worse one. So having equal or higher cost. So repeating the second example. So here, so these sidetrack edges encode deviation decisions relative to the shortest path tree. And then the first deviation decision was made on here in the terminal node. And then we saw that it gave us cost 5 path. And then the next deviation decision can be made or here or there, according to the shortest path tree. And then the second decision that we saw in the example was, adding one more sidetrack edge here, which has cost 7. So you see that, you can read off these suboptimal paths with increasing cost by following this kind of structure here, right? And then it's called a solution space partitioning at this point, because here solution means a set of paths in the problem, and then somehow you can organize these paths in a nice way that it's partitioning the whole space, so that you can run in the end tree search to enumerate one by one. So given a sequence of sidetrack edges, we can decode the corresponding paths using the shortest path tree found by Dijkstra or in the Epstein algorithm or A-star search tree in K-star. So I'm repeating many things again and again. And then we know how to compute the total deviation cost relative to shortest path once we know this sequence of sidetrack edges. So let's say, again, this example is the same example again. So let's say we made a first deviation decision at this terminal node. Then these were the suboptimal path that you chose. And then the remaining choice to deviate is going to be here or there, as mentioned. And then here, there are two sidetrack edges that's coming down and that's coming up. And in this particular example, there's no sidetrack edges over here. So the possible next decision is going to be, you could deviate on here or there, depending on which will give you higher deviation cost. And then for the previous example, we made this deviation from here. And then after doing deviation here, if you look at the shortest path tree, another deviation decision that you can make along the shortest path tree is going to be making deviation here or there by looking at sidetrack edges and so on. So this process continues until you cannot, deviate anymore or reaching here. So any questions? Okay. So we have 3 minutes. Maybe I can finish up to this point and then come back and finish remaining things. So again, this deviation decision can be partitioned. So we can select at which node to deviate in the shortest path tree. And then we can select one of the incoming sidetrack edges at the selected node. Therefore, the paths can be grouped by this kind of tree-like structure, right? So at the first moment, by looking at this graph, the only thing that you can think of is whether you can deviate at S4 or not. So that doesn't mean that you must deviate at S4, because there are other possibilities like deviate on S1 and S0, then might give you lower cost path in the end, right? So you have to check all those possibilities. So there are two possible cases in this particular example where you deviate at here or not. So this branching happens, and this dotted edge actually represent that you are actually making a commitment that you are following this deviation or using sidetrack edges. And in this particular example, there are only one choice, so that the branching is just go down here. And the other possibility was, rather than kind of deviating here, you could think of, I'm going to deviate on here or here by backtracing the shortest path tree, right? Sometimes, of course, deviating here will give you lower cost suboptimal path. So you have to check it, and you check here or there. And at S1, there is another sidetrack edge here, under here, and so on. So, and under this subtree, so if you have arrived at this point after deviating this one, so this is the sub problem, right? So that you start from here and repeat exactly the same idea. So you look at the shortest path tree from here, trace back, and see how you can deviate. In this particular example, there's nothing that you can do further, or you can deviate on these sidetrack edges and so on. So this is how we can partition the whole solution space as a kind of tree structure here. And is there questions, or is it better to continue or just break? Yeah. Okay. Thank you. Mm. Yeah. Mm. Okay. So, hello. So I think we can continue, right? Okay. So in the previous times, we covered up to this point where, yeah, I'm going to briefly summarize. So that in case of in Epstein's algorithm, you can, somehow group your suboptimal passes or plans, kind of this tree structure that, have the kind of optimal substructures that's mentioned in the dynamic programming view, and so on. So this captures most of the ideas of the Epstein's algorithm, but the one remaining part is going to be, before moving on, any questions at this point? To actually make it faster, so the last ingredients that Professor Epstein mentioned in his article in 2014 was that you need to have fast selection method. So if this is slow, then everything will slow down. And I'm not going to go into the details about the complexity analysis of the K-shortest path algorithm by Professor Epstein in 1998, but it's all relying on the fact that you are using very nice heap structures that allow you to do insertion in log time and so on. So if that's not the case, you don't enjoy that m plus n log n plus k complexity. And then on top of that, that complexity result is not coming from a kind of regular heap data structure, but it's relying on very theoretical things that Frederickson's kind of heap selection things that I don't even try to look at that point. But in practice, this view is very useful, but we still have to think about how to do this fast selection on items that you can look at while enumerating the solutions in this way. So two things. The first one is that you have to look at nodes to where to deviate on the K shortest path tree. And then after selecting a node to deviate, you have to choose which kind of sidetrack edge to choose. So it's good to have them all sorted according to the deviation cost in the end. So and then Epstein's algorithm uses heaps to store all those items. I'm going to emphasize some difference later on, but at high level, so you have two types of heaps in the Epstein's algorithm. Maybe this is a little bit different from the paper, from the things that you will see in the paper by Professor Epstein, but it's more or less the same or simplified view of the same thing. The H sub t Si stores the kind of which which node is gonna be giving you the less deviation cost when you make decision to deviate. So these HTSI, you have to define this heap, one heap per every state, and it only stores one root sidetrack edges that's incoming to the each kind of nodes. So this root is not visible in this view, but it's following the convention of the Epstein's algorithm, where he actually defined a graph over the heaps and so on. So it has actually root in the heap data structure, but in this view you don't have such things. But again, so this heap stores which nodes to deviate, so and so on. So for example, HTS4 sorts things like standing on here, you can deviate here, 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 3 points. But here there's no sidetrack edge, so you can only have 2 items to deviate. And then you need to know which one is gonna giving you a kind of less deviation cost. So that's defined by delta here. So here it says that deviating here is cheaper than here, comparing the first sidetrack, incoming sidetrack edges to this S1 or S4 and so on. And then the other data structure is storing the all incoming sidetrack edges per each node. In this case, S4 has only one, S2 has 2 sidetrack edges. So if you see this example, then you have to sort them by their deviation cost. So for example, if you see this sidetrack edge, so it's about 1 deviation here. So S1 to S2, the kind of path cost detouring this sidetrack edge is going to be 3 + 1, and the cost along the shortest path tree is only 2, so delta is 4 - 2, which means 2. And then this one, if you follow this sidetrack edge, then deviation cost is going to be 2, 1, 2, 5. But the cost along the shortest path tree was 2, so delta is 3. So these deltas are all this cost deviation according to relative to the path in the shortest path, and then using that one sidetrack edge. So by having this, you know how things are all sorted on these sidetrack edges. Any questions? Yeah.
Yeah. Is the use of this data structures, is this affecting the worst case complexity or the expected performance, or yes?
At this point is the conceptual view. And if you implement this in a kind of many non-traditional data structures, heap-based ones, then you can achieve the theoretical kind of worst-case complexity bound. But I'm going to comment about what happens if you're not doing that later on. And in the case the planar implementation, actually, we didn't actually implement the kind of that optimal data structure that guarantees you that a nice worst case complexity at this point. Yeah. Yeah.
More concerned with
Mm-hmm. Average, maybe.
Yeah, well, look at that's all.
Yeah.
They work very effectively almost all the time.
Mm-hmm.
Very low problem.
Mm-hmm.
But that doesn't change the underlying complexity class at all.
Uh-huh.
And so I'm asking the same kind of question here.
So
to the point where you've got a certain worst case complexity, but in general we do way better than that.
Oh, of course, I'm gonna talk about that maybe 2 or 3 slides after this one. I have a comment about that part. Thanks very much. It's an important part. So again, in the end, what you have is this, from this conceptual view, you have this view on arranging everything that came out from the heap structures. So at high level, in the end, what we obtained after doing this was that you organize all the sidetrack edges in 2 types of heaps, where each type of heap has to be defined on each node or state in the state space. And then by using those 2 types of heaps, you actually construct a successor generator for this search space. So Epstein's algorithm actually defines a search problem on enumerating the suboptimal paths or plans, and you can read off one by one by looking at this kind of path cost, because this in the end you run again the kind of diextra on top of here again, so that you can enumerate suboptimal paths according to the value of each node, and then the value of each node is coming from these deltas. Adding up deltas along the path will give you the total deviation cost. So at this point, any questions, or just can I just move, or yeah? I'm skipping something here, so if you have question, then you can ask. Okay. Later on, if you get more interested in this, then you could ask a question later on, and so on. So this is the last slide on K-star planner. So there are many modifications made in actual K-star planner. So first off, so on Epstein search space for K-best enumerations. So in Epstein's algorithm, it actually generates solution paths from a graph over the heaps. So if you have chance to read that paper, you feel like it looks very different, but essential idea is the same. But in case of K-star planner, it traverses the tree that's shown in the earlier slides. And then it's regarding the complexity. K-star planner doesn't do this fast selection with the complicated heaps, but it still maintain this dynamic programming views. And if you talk about usage of the heaps, so to implement the Epstein algorithm correctly, you have to have 3-array heaps and heap graphs and heaps storing the kind of pointers and so on. But none of them is existing in the, let's say, C++ STL kind of libraries. And you have to choose to implement everything in C++ compatible to STL, or you have to compromise to use something else. In K-star planner, we just used a linked list that's storing the pointer to the sidetrack edge object. So it's a kind of doing better than pure kind of other approaches, but this is necessary choice to handle pointers. So the search space is really defined over using the pointers on all the objects here. So that's one way. And then the worst case complexity was kind of assuming that your branching factor for the graph can connect everything, so dense graph. But in case of planning problems, each node branching factor is very limited. Pretty much you can say it's bounded by some constant, right? That's the point where you can kind of compromise to use this kind of non-optimal heap data structure, but linked list instead. So yeah, and then yeah, pretty much you don't really get 1 million sidetrack edges per node. Yeah.
So is it really worth it to implement all this crazy stuff about the Epstein? Like, what is the? I mean, you have this 2 phases, right? A star, and then you do the sidetrack Epstein algorithm. So do you know from your data or the empirical evaluation, like what is the harder part, like doing a star or really like extracting then all the plans?
So are you talking about, is it worth implementing all these kind of things?
Because I don't like if the Epstein algorithm always like takes only a portion of the time, and the other phase takes almost everything. Like then it's not really worth it to.
That's right. So in our evaluation, we see plans up to 1,000 only, or maybe 10,000 at most. At that point, the Epstein search space has very small it doesn't really worth to investing time on here. But let's say if you really want to go for million, billion, trillion plans, then that makes difference. And somehow branching factor is very high that, somehow one node connects to 1,000, or that's not happening in classical planning problems anyway. But if that's the case, then it will make difference. But in case of PDDL planning problems, it's not happening. So we just stay at this point. Yeah. And STL implementation, compatible implementation, or heap graph or something like that is going to be something take time. And then to the best of my knowledge, this Epstein algorithm is not implemented in that way. Yeah, it's a kind of theoretical paper. Yeah, so there's a compromise. And another details. So on original K-star, so it performs Epstein's algorithm over the expanded nodes in the A-star. So it's a delicate, but the difference between expanded node versus the generated node is that nodes that came out from the frontier from the A-star is all sorted nicely, but on generation, it's not that sorted well. So that K-star search, one nice thing about K-star search is that if you just staying on this expanded node, smaller nodes, then you can switch A-star and Epstein smoothly, so that you don't have to really reconstruct the search space for the Epstein again and again. But that comes with the cost kind of things, that it's always good to work with generated node if you can when to search. And K-star planner actually doing that, and therefore it restarts Epstein algorithm after switching back from A-star to Epstein. And again, we are only looking at a small number of plans in applications, so that this doesn't really give you any overhead. If we have to build billion, trillion kind of plans, then it will make some difference. But we under this kind of application regime, it doesn't really matter. And then, of course, rather than implementing Epstein, we implemented lazy version of the Epstein that saves you some time in the end. And then for the adaptation of PDDL planner, so K-star has to have one single node and then one terminal node, so that PDDL problem has to be transformed in that way to have one single terminal node. And then another important thing is that heuristic kind of quality, rather than computing the heuristic on the transformed problem, just compute the heuristic on the original problem, and then transfer that number back to the transformed this problem performs much better than just naively just creating heuristic from the transformed problem. That's very important part. So this is the end of the K-star search, and then maybe before finishing this, if you have any question, then you can ask. Yeah. Otherwise, I can move to SimK. Yeah. Okay. Thank. Yeah.
I think I have a question. You say you're transforming the input to the real problem at single terminal node.
Mm-hmm.
Is that transformation more than something you have to apply to the specification of goal states?
Yeah, so you have goal state, and then you have one terminal node.
Right.
So that's changing the problem. Yeah.
Okay. Because the reason I asked is because of the second bullet, you talk about the transformation preserving quality of existence.
Yeah.
You're making it essentially a fairly trivial change to the.
Yeah.
Would you expect the heuristic, the value for those heuristics to change under that very many transformation?
Based on the experiment, it had impact on the overall performance. Yeah. So that's what we learned from the Okay.
It really heavily depends on the heuristic. Like there are some derivative results. Like for example, goal count you could use but I think that of course that's not an optimal heuristic, but HNX tries to fix it. And I think Alan cut and then but sometimes all the type breaking process and everything. Okay, no, that makes sense.
Yeah. Thank you. Yeah.
Okay, then let's go to the last technical part, but fortunately, SimK stands for symbolic search, and it luckily is a bit easier than Epstein's algorithm. That's probably why I did it. So in general, what we have just seen, or what a general theme in classical planning, is that we have a problem, what we can call, or I call it here, the state space explosion problem. Start with initial state, and we somehow try to find path to a goal state, but we realize, oh, there are so many possible states in between, and we can't handle them, like exponentially many in the model, and yeah. And one approach, and we have just seen that with K-star, but it's also with A-star and really best first search and so on, it's always to use distance estimation to the goal to check basically, or to try to prune or not to ignore some states. Like, I don't know, normal heuristic search, right, just says, okay, I only have to consider now this state because I don't have to consider those states. That's the most common paradigm to find or to handle the state space explosion problem. But there is also another paradigm for optimal planning, which is called symbolic search with decision diagrams. And there the idea is of handling all of these, the state space explosion problem, by trying to not explicitly represent these states, but to compactly represent them in a symbolic way. So basically in a formula or with decision diagrams. And it is known that it's pretty good for optimal planning. Like, it's somehow has complementary strengths to heuristic search. So in some domains, heuristic search is better in some symbolic search. So we know that it's good for finding a single plan, but I try to convince you or to show you that it's also really, really good to find multiple plans. And just to put that ahead, the reason is that you only need really minor modifications because you get a lot of things for free. So SymK is just a planner name, but yeah, I'm not really good at naming it. We just invented in our paper to say, okay, we do symbolic search for top K planning, so for finding multiple plans. So I will somehow use it interchangeably, but of course, yes, SymK is just an implementation. So symbolic search, as I said, is like originally in planning introduced to finding a single plan. And the main idea is to exhaustively do an exhaustive search with concise data structures. And there you more or less enumerate all the reachable states from the initial state until you find the goal state. But if you continue, you also, like, you just find goal states and goal states after goal states. And the nice thing about that is, about this whole paradigm, is that you don't represent paths explicitly, but you represent them implicitly. And we have seen that with K-star, that it's really hard, like this whole sidetrack thing and so on is always to avoid explicitly represent everything, how you can reach a certain state, because that becomes really infeasible at some point. And here already for symbolic search for a single plan, you get for free some compact representation. Like, you just represent which states I have reached with which costs, and you don't really know how you have how you came there, but then you do a plan reconstruction to extract the plan. And that's the reason why it's a really promising candidate for finding multiple plans, because you do an exhaustive search, you to some extent have to do that, and also you're implicitly representing plans. And yeah, as I will show you, there are only 2 minor modifications to actually generate all plans in an anytime behavior with increasing costs. So the outline for this section now is that I will give you a high-level summary on finding a single plan with symbolic search, and forward, backward, and also bidirectional search. And that's really the key to understand how we can find multiple plans with that. And then I will show you how to modify symbolic search algorithms to find multiple plans. So symbolic, and of course, if somebody has questions and I'm too fast or things are not clear, please just raise your hand. So symbolic search, and I already said that the key idea is that you don't handle individual states, but you handle sets of states at the same time. And how to do that, or how we do that, is that you can represent a set of states by its characteristic function. What does that mean? We have a vector representation with variables, right? And the formula x and y, you can just say that's a representative characteristic function to represent all the states where x and y is true. And that's really compact to write down, right? But it is potentially millions of states, because there can be millions of states where x and y is true. And in a similar way, you can represent actions with association relations, also with logical formulas, just saying what has to be true before and afterwards. And then you can modify these sets of states. And with that, you can do essentially forward, backward, and bidirectional search because you're talking about sets of states, not individual sets of states. The key point here is that we somehow have to represent these formulas. And for that, in symbolic search, we usually use decision diagrams. Here now, the most common one are binary decision diagrams, which are just, yeah, they have internal nodes which decide which values certain variables have to have. And then when you end up in the end at the one node, it says, okay, this formula, if you follow this path, is represented by this decision diagram. So this decision diagram here would represent the formula X and Y, because we follow here and then we say the dotted nodes are always the variable is false and the solid arrows are it's true. So here it says X has to be true, then we come here. If Y is true, then we come to 1. So X and Y is represented as a formula, and here it says if X is false, it's to 0, and so on. But to understand symbolic search, it's probably the best thing to really try to see it as just we have sets of states we can manipulate and transform at the same time. So we don't have to pick all the individual states. So how does symbolic uniform cost search work? The general idea is that we always have a set of states, Si, with the minimum G value. So like you would have it in your normal heuristic explicit search, that you have an open list, but instead of considering a single or popping a single state with the smallest G value, you just take all of them. Then you do a zero cost press first search. So if you have zero cost actions, you just apply all the zero cost actions and you extend your set of reach states until you can't reach more. And then you apply the transition relation. So basically the actions with different costs. You compute the costs which are reachable by that. You have here the values, the certain costs. So for the states were reachable with cost I. And now if you apply some actions cost C, the presiding cost is I plus C. And then you insert it in the corresponding cost bucket. So in the set reachable with these costs. And always if you expand, you check if there is contained a goal state. So here at the bottom, we have a depiction of how that works. So in the beginning, we start with a singleton set, the initial state, with cost 0. We know it's reachable with cost 0. And now we check if it's a goal state, of course, but let's say for this example, it's not. And then we do this zero cost fixed point computation. So we generate all the states or the state set containing all the states reachable with cost 0. There we check if it's a goal state in there. And if it's not, we apply all the cost actions. Let's say here we have some actions with cost 1 which are applicable, and they would lead us now from this state set, and they are all handled at the same time because they are formulas. They would reside in the successor state S1. These are the states which are reachable with the cost of 1 from this state set. But we also get some with cost of 5. Then again, we take out or we consider the bucket or the state set with the lowest cost. It's the G values. We apply all the zero cost actions. We apply all the, we apply again the cost actions. So now we have some here with cost 2, but here it could be that some actions with cost 4 are applicable and we just add them to the set of S5. And now let's say, okay, we now would expand state set S2. And here now we can just check if there's a goal state included in the state set. So logically, you just would do something like AND the goal formula, and you check if this formula is satisfiable or not. And with this decision diagram, that's an easy, like, it's in the size of the decision diagram, so it's an easy check. So let's say we find here one state, but it could be multiple goal states, right? We do everything at the same time, so we could also find multiple goal states. There's already a hint why it's really good to find multiple solutions. But just for one, we say we pick one of those. So now we talk about explicit states, and now we do a planned reconstruction, because we were here handling all the states in the state set at the same time. So we actually have we just know we can reach a goal state with cost 2, but we didn't know how to come there. So we didn't represent the plan or the path explicitly. What you now do is you oppose your search direction. So you do a regression here, a backward search, and you just check, okay, you go over all the possible actions and you check which state would have led me to this state. So you compute the predecessors, and you always check if this predecessor is in one of the states, as before. So basically, you do some kind of greedy heuristic search with the perfect heuristic you have computed. So let's say here 3 actions could lead to this state: a brown one, a blue one, and a red one. And we see here that, for example, the blue one, even though it could lead us to a state if we apply the blue action, we haven't considered it before. So that can't be the way how we came there. But the red one, we realized that it's part of the state set which was reachable with cost 1. So we picked this one. Is it red? It's orange, right? Sorry. Yeah, doesn't matter. And we continue that. And we do again, go over all actions, and we check how we came there. And now this is one node. Let's say it's the blue one, and that was reachable with cost in this outer layer. So we do again, check how can we came there. So we basically trace back how we came there. And now we see here until we reach the initial state. And by that, we have reconstructed the plan.
So two predecessors, one in S1 and one in 0.
Normally, you choose any of those. I mean, if you want to do it as efficient as possible, you can be greedy and try to jump directly here, but usually you just pick one of them. But yes, it doesn't matter which one. But
looking for one.
If you're looking for one plan, exactly. But you see here that all the machinery to find multiple plans is already there. So if you, that's one of the minor changes you have to do if you want to find multiple plans. You just check for all actions, not stopping when you ended in initial state, but then just you check the other options and you just do an exhaustive search over with the perfect heuristic, basically, in the backwardation. Yes, I mean here it's greedy search because you have the perfect heuristic computed beforehand. That's like the point. And yeah. Further questions to that? But the real insight here is that we don't store these passes, right? And that's why it's efficient. Because otherwise, like you would store all the different ways of how you have reached the state, and that could be really kill you in some sense of computational thing. Yeah, and then, okay, you can construct the plan, which would be here now, the red, the blue, and then it should be orange. So, but I'm not sure if it's showing here correctly. All right. So that was the forward direction, and really quickly, you can do also the backward direction. Why can we do that? The reason, or how can we do that? First of all, you start with the set of goal states, and then you use, instead of the image computation, the pre-image computation. And there are some challenges usually in planning for doing backward search, which is why it's not really that popular. The reason is that you have multiple goal states, and also that you get sometimes partial states, again, representing multiple states. If you do a regression, right, you can have multiple predecessors. So applying an action always leads in a state, always leads you to an individual successor state, but doing the regression, it always can lead to multiple states. But because we talk about sets of states in symbolic search, we get it for free. So we don't care that we talk about sets of states. That's a really cool thing here. And the next thing is spurious states, that are states which are not reachable from the initial state, but could lead to your goal state. There can be many, but there are tricks to handle them, like state invariant pruning. But in general, for our work, it's not that important. I just wanted to mention it here, that you have to be a bit careful, because otherwise your backward search can become really inefficient. All right, so with backward search and forward search, the obvious ways to do bidirectional search, and that's the last slide on finding a single plan, I promise. And how to do that is basically you do forward and a backward search at the same time, and in each time step you decide if you do a forward or a backward search, and you stop when the costs from the forward and the backward direction exceed, plus the minimal cost of the operator exceed the solution you have found. So we start with the initial state again, as a set of state, and here with the goal state, goal states, that's the point, right? Here, like you have only a goal formula, it could be your goal is X, then it's half the state space, but it's nicely representable as a formula. Then you do a forward search, you do this zero cost loop, and we have seen that before, right? You find here something with S1 and S5, and then you do a backward search that you generate all which are reachable with cost 0 in the backward direction, and also the other direction. And now let's say we have found here collision. So how do you find a collision? Basically, if these two state sets, or if two state sets you have found have a non-empty intersection. But here you see that now the plan you would have found has cost 10, because it takes you 5 to come from the goal state from the goal states to here, and it costs you 5 to come from the initial state to here. So you are not allowed to stop, but you have to continue until actually you want to expand this part. So you want to expand something which is more expensive than the solution. And then, as before, you pick one state of this intersection. So you just extract it from the formula or from the decision diagram. You do the thing we have seen before, like opposing the search direction. And in a backward search, now you do a normal forward search with the perfect heuristic. And yeah, let's just say here, for sake of simplicity, you pick just the action which led you from here to here with cost 5. And then you have found a plan, which would lead from the initial state to a state here, to a state here, and to a state here. Are there questions to that part? It's basically you have two formulas, right? And you do an AND. So it's just, I mean, they are in form of these decision diagrams. So you do a logic AND, and then you check if this set is empty. And because it's a decision diagram, you have some properties that this is polynomial in the size of the data structure. So it is pretty efficient to do that.
The cost of the polynomial?
In the size of the...
Because for every set, you might have different costs.
Okay, that's a good point, yes. So either there are two ways to implement it. Either you have to do it with all these cost buckets, but what we do in reality is that we also maintain a set of states we have already expanded in both directions. So a formula saying combining all of these sets, and then you just intersect it with this, and you check if you have found a collision or not. And then you detect where you have found it. But yeah, in general, you have to do something like, okay, I have no new state set, and I have to intersect it with this one, and with this one. So it scales in the size of the different representation is. Does that explain it?
So for every state, like let's say you have like one state expanded in backward search.
Yes.
Then we need to see what you have in the forward search for that exact same state, right?
Yes, but the point is that like we are representing multiple states. So each of this set here is represented by one formula. So we are not talking about individual states. So it's just, I don't know, like the formula X and Y in the backward direction and in the forward, which represents a lot of states, everything the X and Y is true. And then you have a state in the, or one of this one would be X and Z. And then you do an intersection, you check if there is an intersection or not. So you can do that for all of these states in the same time. Further questions to that? I know it's a bit hard to imagine to handle multiple states at the same time, because we always have this paradigm of talking only about a single one. But yeah, of course, I mean, also there's no free lunch, right? These decision diagrams can be huge, like they can have tens of millions of nodes. But in practice, and that's always our hope, is that they are pretty small and you can handle those. And there are really good libraries, like you actually can handle decision diagrams with millions of states, millions of nodes. All right, so that was, now you know how to find a single plan with a symbolic search. And we will now, or I will try to convince you now that you don't have to do too much work to find actually multiple plans or to enumerate plans in increasing cost. So there are two main things you have to do. The first of all, you have to perform the symbolic search without ignoring states you have already seen. So I have skipped that a bit. What you usually would do in symbolic search is that if you have already expanded the initial state, you would not consider it here again. Like you would just cut it out again on a symbolic level with the formulas. But you have to do that to find all plans. We will see in a second why. So just you keep all the expanded states such that you know, okay, the initial state is, for example, reachable with cost 0, but it's also reachable with cost 5 and reachable with cost 7 and so on, and also for other states. And further, once you find a goal state, you not extract one path how you came there, but you expand, you extract all of those. So you do an exhaustive search over how you came there. So let me give you this really stupid but simple example with the iconic Cripper domain. So we have here a Cripper, a ball, and 2 rooms. This is the initial state, and you have actions like pick up, then you come to S1, you've picked up this ball, you move to the other room, and you can drop it. So that's the whole state space, and this one is the goal state. And how symbolic search, and now we only consider forward search, would work for that to find multiple answers. We start with the initial state, right? So the formula representing the state. And then we expand the state set and we consider all states reachable with cost 1. So I consider here unit cost. So each state reachable with cost 1 from here is only this one, the S1 state. So our set of states reachable with cost 1 is a single state again. And okay, yeah, good point. It is a modification you can't, like that's the full transition. You can't move without having the ball in the hand. That's just to make things easier here. So you have to have the ball in the hand. And you also can move just from S1 to S2, so you can't move back.
The only thing it's not showing is what the talking about symbolic search.
Yeah.
Using decision diagrams to represent. So formulas represent types of very large sets of states.
Yes.
This example is simple enough to not show that.
Not yet. In the next one, we get multiple states, but I agree. Yes.
But yeah, what the actual formula is.
No, I don't talk about it. Like the actual form. Yes, that's true. The actual formula to represent that would be ball at room A and gripper empty and something like that. Yes.
So for there, it's a complete science.
Yes, exactly.
Yeah. But that weakens as before.
It really heavily depends. So these formulas represent decision diagrams and they are reduced and normalized. So they are not really extracted, like they are not. Okay, let me go back to the decision diagram thing. Like, it's a good question. So here, when I said this is represented formula X and Y, there could be, if you have two variables, there could be 10 more variables and you're not talking about them. So yes, the initial state is really talking about each variable, but then if you extend it and you're not talking about a single state anymore, but multiple ones, this one can be, or that's the hope, is much more compact than representing all the states at the same time.
That's exactly what I'm asking.
Yeah.
If you have 10 other variables, the question is which of them
You need to branch over.
either have to remove from the decision diagram to regressing to the search.
Exactly,
Or
but
regressing.
that's like more on the decision diagram theory, and there are strict, like there are rules how to do that, and that you can do operations like intersection and so on.
Mm.
And I mean, on a conceptual level, you don't, if you work with this libraries, you don't have to care about it. They do it for you. Yeah.
I'm asking something dumb.
Yeah.
If my cost one action is if X and Y are true, then in the state following that action, Z
Yes.
is now true.
Yes.
And presumably you'll have to.
Then you have to branch over it. Then it will be a node in there. Yes.
Exactly.
But-
So that conceptually is a way of how are you manipulating.
The formulas, basically.
Exactly.
Exactly. But these formulas are always try to be simplified in the form of decision diagram. So it could be that after applying some actions and you put some states together, that you don't care about the value of Y anymore. So that could also disappear then in the decision diagram.
I'm not asking about the
Okay.
you're even doing this.
Yeah.
It's how you're manipulating the, you know,
So
BDDs, how you're manipulating the propositional formula that's actually coded.
like how we apply the actions, you mean, or? So I mean,
Or it's how you represent the state that's you either regress to across an action, or progress to by the application of that. We're getting a little off.
State 1 or state 2 or state 3 and state 4, and then that's the one it equals to the state.
I mean,
That's it.
I mean, you start with a formula representing initial state, right? That because, and then you have these, you can represent actions as transition relations that are basically pairs of, like that's again a formula talking about how your predecessor states look like and how your successor state look like. Exactly. And then, yeah, I mean, you do an intersection with the preconditions that have to be true. You check which states are applicable in your current state set. You have variables talking about the effect. And in the end, it transforms your formula representing your current state set to a formula representing the successor states.
And it's normalized.
Yeah.
It's not linear, right? It's not like you look at one of them in the middle and say, I know what states are.
I don't know if this is be like.
But yet, like these formulas can become larger and smaller. Like it really depends on what states you're representing. Sometimes it can hurt you to add a state to the state set, and sometimes it can be good to add a state. Like it depends on how nice you can represent this formula. Okay, so coming back to the example, with cost 1, you can reach only that state. So you get this state set. And then from S1, if you expand this one, we can reach with cost 2 actually 2 states, S2 and S0. Because from S1, yeah, we can either move here or we can drop again the ball. And here you see already what I just said before, we're not allowed to close state, so we are reconsidering the initial state again. So it's reachable with cost 0 and with cost 2. Then we expand this state set, and here we get again 2 states, which is in the first place a bit surprising, but if you look from S0, only S1 is reachable, and from S2, only S3 is reachable, so we come over here. And here now we have a goal state, S3, and now we do plan reconstruction. And here basically now we trace back how we came there. So we realized with the regression over this formula, or here we pick the explicit state, that with drop the predecessor was S2, and with move the predecessor was S1, and with pick up the predecessor was S0, so our plan is pick up, move, drop. But if you now want more plans, we continue with that. And now if we expand this state set, we can reach again 2 new states. This costs 4, because from S1, we can reach S0 and S2. And from S3 again, actually, we can also reach S2, but the same state, we already know it. There's no goal state in there, so we can't expect a new plan. But if we continue, we reach this state set here, and now we realize, okay, again, we found a goal state, and we can reconstruct the plans. And here now we can reconstruct the plan, pick up, move, drop, pick up, drop, which is a bit stupid, right? You pick it up, you move, you drop, you pick it up, you drop, but that's how this exam is. But also we can extract another plan. So we can now extract also that we came there by pick up, drop, pick up, move. So we do this stupid repetition in the beginning. And we continue with that until we have found enough plans. That's the main idea behind that. And always here, like also I talked about explicit state, they are formulas, and you just extract plans once you find a goal state. And you can also have here multiple different goal states. Any questions to that example? No, that's good. Yeah, we just can continue. But yeah, so actually, what I just showed you is symbolic search for finding multiple plans. So what we do is we iterate plans with increasing costs. We have a really nice anytime behavior. It's not that we have different phases and always have to shift between those, but it's really like we do this forward search, and always we account on the goal state, we extract the plans. And for top K planning, we simply stop when we have found K plans. And for top quality planning, we stop when we exceed the costs. But we also can stop when we know that there are no more plans exist. So it could be right that there's a finite number of plans, and K is potentially larger. And here I have to say it's a bit tricky how to find out that there can't be no more plans. But the general idea is that the region, like you have an open list, or the states you're still supposed to expand. So here, for example, it would be something like that, or yeah, the states which you still want to expand in the future. And if those with all the reachable states you want to expand in the future form a fixed point where no goal state is in there, you can basically prove that you can stop. But it can be really exhaustive, and yeah, it can in some domains be really hard to prove that there can't be no more goal paths. But in general, our algorithm is complete, so at some point it will tell you there are no more plans.
Is it possible to have those sort of pop out? So,
Yes, I think also in our practical thing. So you can either say, yeah, you can have, of course, yes, you can have both. Yeah. All right, so with this example before, with this one, you already seen these plans are pretty dumb, right? And that was why we considered at some point loopless top K planning or loopless plans. Michael already pitched it. Because the point is, okay, why do we, not even a script example, I can tell you that there's the domain, the elevators domain, where it's about transporting passengers. And we generated there, I don't know, the top 10,000 plans. And actually there to board a passenger costs 0. So all the plans we have found was always to board the poor passengers multiple times and unboard it from the elevator. So the plans were, okay, passenger 1 should go into the elevator, we bring it to his floor. The second plan was passenger should go in the elevator, he should step out, he should step in, and so on. I mean, that makes no sense, right? And so we were considering ways to generate and loopless plans. And the idea was to, the first and most naive way was to request a sufficient number large of plans. So basically K to infinity, enumerate all the plans with increasing costs. And if the plan is loopless, so it's a generate and test plan approach, then we use it, and otherwise we discard it. And there are pros and cons to this approach. So the first one was, it's straightforward. You don't have to do much. It's a sound approach because we only consider plans that are loopless. But the performance strongly depends on the number of discarded plans. So if you have a lot of this loopy plans, you discard all of them, but you generate them. And also it's not complete. And here's a tiny example why. If you have 0 cost actions, here are actually that these are 3 different operators. That's the initial state, that's the goal state. In the brackets are the costs. So here, an optimal plan would be to apply operator O1 with cost 1, which leads you here. But the next optimal plan would be applying O0 and then O1 and then O0, O0 and the 1. Our planner would generate it over and over again. We would always discard it, and we would never realize that there's a plan O2. So there's a different approach in our planner or for symbolic search to fix that. And the idea is to modify the plan reconstruction I just showed you. And there actually you just should keep track of the already visited states and ignore them during the plan reconstruction. So here's an example. We start with SG, so our goal state. In the beginning, we have not visited any state. Then we do here this plan reconstruction step. And let's say we can come to here with S3 and S4. And then we consider, okay, we have already visited SG. So we would ignore it, but here in this path, like both are different. Let's say we pick now S3, we come over here, and there would be, we could have come to S3 by S1 and SG, but we realized, okay, we have already considered SG, so we just ignore it. And by that, basically, yeah, you can't generate any plans with loops. And the point here is that you can prove then that this approach is sound and complete and would not generate these loopy plans anymore. So it generates only relevant plans, but it's a bit more complicated, and you can have an overhead because you have to make this bookkeeping, do a plan reconstruction, and can be worse than doing the naive approach of before. So that's now my last slide. In general, what I just showed you is for this loopless top K planning, I see it a bit more as a general approach because what we already said is you want multiple plans because often you don't know specific properties you want from the plans. And you can do that in different ways with symbolic search, but also with your planners, of course, at least to some extent, because what you can always do is you request a sufficiently large number of plans. You enumerate all these plans with increasing costs. And I think symbolic search is really good here because it has any time behavior. It doesn't matter how large the K is. I think for iterative for bit iterative is the same. I think for K-star it is a bit depends a bit on the K you set. And then basically you just check always if your plans have this desired property or not. And if you only want one, then you stop if you have found one, and if not, you continue. But optional, and that's the cool thing in the symbolic search thing, you can actually make it more efficient by ignoring certain states or certain things during the plan reconstruction. So you don't have to generate all the plans, but you can stop early, and that was what I just showed you with the loopless thing. So some application examples where we used, I think, my planner, but maybe also some of the IBM guys. Of course, it's not as flashy as the IBM applications, but I still want to mention it here. So of course, you can satisfy complex user preferences using this general approach of producing plans and then checking them for the properties. And actually, where, for example, loopy plans are important, so sometimes you want them, is for finding hierarchical task network plans. So you can, some fragments of planning, you can model it as classical planning and throwing away some aspects, and then you can generate multiple plans and just check if it's for the original model already, if it's of a original model plan. And further, and that I found pretty cool, is you can crazy stuff. So we did use my planner for finding the longest loopless plan in a competition of the combinatorical reconfiguration challenge. So there they wanted to know how you can reconfigure, for example, grid networks like energy networks, and what's the longest way of doing that. I'm not sure why they were interested in that, but they wanted to know it. And you can use top K planning for that, because you can just enumerate plans over and over. And actually what we did is here, we just did a plan reconstruction when we found a new goal state with a new cost, like with a higher cost. And we reconstructed one of those, which are loopless, and then we continued that. So we produced longer and longer plans. And actually we won the challenge, I think, not only in this track, but in the longest loopless plan track, we won it twice, and I think with a big margin. So yeah, I think really there's a lot of things you can do with this finding multiple plans, and adapt it to be even more efficient to only generate plans you really are desiring. Are there any questions to that part, or comments, research ideas? Okay, then I think we can come to the hands-on. So it will be, yeah, I mean, I'm not sure how long we will do it, but just the first thing, all of our planners are available on GitHub, and also, so yeah, the forbid iterative, K-star, and SumK. And there, I think there are everywhere also explanations how you can install them. Yes, sure. Okay, so okay, so it was not my work, but I think Daniel Höller said that, or like showed a way of casting HDN plans into classical planning tasks, and there the solution space is over approximated. So not every plan is really a valid plan to their HDN problem.
Right. Okay, so you're saying there's a transformation.
Exactly. Exactly. And every time you find one, you just do a validation if it's a real HDN plan or not.
And that's what you use. Okay.
Yeah.
Got it.
I mean, you could also do it, for example, with numeric planning, right? Just ignore the numeric aspect. Probably will be not a good approach, but yeah, I mean, this over approximation should be not too crazy. All right, so everything is available on GitHub, but we also provided, or all of our plans have also some Python bindings, and we generated some notebooks. Just as a disclaimer, if you really want the raw performance with all the latest features and so on, it might be a good idea to install the standalone planners. But if you're just interested, I think for multiple problems also already fast enough to use the Python frameworks. And I'm not sure, do you want to start with your notebooks to show them, or do we want to do that? Yeah, Michael.
Just switch to the next one.
It's a Mac. I don't know how to do it.
Yeah.
Right. So
Okay, so
maximize the window or something. Whether it's not already maximized.
how do I do that?
It's usually a double click. No? It's already.
Maybe can you also zoom in the
Yeah,
or zoom?
like, so if you want to zoom in, let's show you something like this. Come on, plus. Large enough?
Okay, so I think the K-star and forbid iterative are pretty similar. Some case a bit different with the Python binding, but the general theme is that you have to install a package. So here it's forbid iterative, and yeah, we have here fixed here the the number of okay, I think here I run it, right? Yeah, okay. Okay, I think we don't necessarily have to run, but okay, so you installed, we have fixed here the version number that it will work, but okay, you install it, and now let's consider again a gripper example, where you can have, like, that's the normal gripper we have in our planning task, now with 2 balls. Of course, it's not the most interesting problem, but it fits the scheme of showing which plants we can find. So initially, 2 balls are at the left room, we have here the 2 grippers, and the goal is to move the 2 balls to the right side. In the next cell, actually, we are downloading those, and here's a function to just pass the output of the planner. I think it's not too important what's going on here, but here are then the paths to the 2 files, and we are importing the forbid iterative planner. And if you look here now, you see the diverse, how to use diverse planning for that. So actually you call here the package, the forbid iterative planner, and you just call plan diverse agile, I think it's called, right? And you put in the domain file, the problem file, and here it's number of plan bound is 10 and a timeout of 30. So I guess the number of plan bound means we want at most K plans. Okay, that's the K. And then actually what's happening here is that's the function we've seen before, that we found 7 plans of cost 2 and 9. No, other way around. Okay, we found, yeah, that's the next.
Yeah,
We
this
found-
point was, right? So this.
Okay, we found this cost 7, we found 2 plans, and this cost 9, we found 8 plans. And let's look at the planner output. Actually here, you can see the 2 plans with cost 7. It's pick up and move, drop, move, pick up, move, drop, and so on. But if you, for example, want unordered top quality planning, you can call a different function here from the planner, plan unordered top PQ, and let's see what's written in there. Here we have the quality bound of 1.5. That's actually here, I think, is constant, so it should be not worse than 1.5 times the best plan cost. And number of plan bound is 10,000. And now we see here that it found more plans and actually also some better plans than before. And yeah, I think the scheme continues here with subset top quality planning. So here we are not considering all the plans, but just those which are not supersets of plans. And you see that some of the plans had disappeared, right? Like here before we had a huge number of plans which were. Michael? Yeah, so it's just, I think here it's just saying we want 10 plans. So, and then I think that's a cool thing about Michael Planner's package. They also have a plan visualization. So here now you see, okay, now it becomes a bit big, but here you see actually, I think that's the initial state, right? Like the robot is at room A, 2 arms are left and right, and sorry, they are free left and right, and there. And now you see like which action leads to which successor state and how these plans are branching. And in the end, I hope they all, yeah, will end up in the goal node. And yeah, I think, I mean, now you also have an interactive thing to really click and decide which one you want to use. Are there questions to this notebook? So I think it's pretty just like it. If you want to do research and modify the algorithm, you probably should use the GitHub repository. But if your application is just interested in finding plans and then taking some of those, I think that's the way to go. So K-star is probably pretty similar, I guess, right? So yeah, you see it's everything more or less the same, just you install a different package. Here the K-star planner, and you import it. And then, yeah, here that's now top K planning, and we're requesting 10,000 plans, and you already see here that because of the problem thing that you get, I don't know, like 696 plans with cost of 9, and probably you don't want to provide all of them to the user because it's just different versions of it. So yeah, that's one of the reasons why we look at different computational problems. And the same for top quality. Here you can just say we want say up to 1.4 times the best cost of the plan. So up to 7 here, and for another top quality, it's the same. And then let's go to the last one. That's the SimK planner. And here I should say it's integrated in the Unified Planning Framework. That's from the European Union, where a lot of planners are integrated. So it is a bit different from the integration. But same problem, you include all of those. And here that's what we did before, that we have a validator and also like we check the plans. And then, and that's the point, like in this unified planning framework, you can say, okay, I want a one-shot planner. That basically means a planner which just tries to find one plan. And here we choose SimK with the optimal version. And then we get different results that, so we do here the solve, and then we get different status from the result. And here we say if it's positive, then we want the cost of the plan. And the output here is actually that we find the plan, pick up, move, drop, drop. But what I like, and that's why I want to highlight this here, is that using this planning, this unified planning framework, you also have an iterator. So before you were asking for 10,000 plans, and then you were waiting for the solver to provide them. But you can, with SimK or in this unified planning framework, you can also say you want an anytime planner here, and you want 3 plans, for example, and then it really like provides you an iterator. So you don't have to wait until it finds all 3 plans. But as soon as it finds one, it gives it to you, and you can say, do stuff with it, right? You can either continue or stop or whatever you want. And here, yeah, now we find 3 different plans. And you can also find all optimal plans. It's more or less the same. It's just that you say we want an anytime guarantee of optimal plans here. And yeah, then you see here that it finds actually 8 plans which are optimal, but again, in an anytime behavior. And if you want to find, that's now top K planning, 50 plans, you just can give a parameter that you want 50 plans. And here you see this iterative nature. So after it finds 10 plans, it tells you, after it finds 20 plans, it tells you that, and you could stop early. And then it tells you, okay, there are 8 plans with cost 5, 8 with 6, and so on. And the final thing is the loopless thing. So you can add a parameter that it should be loopless. And then, yeah, it just finds 50 plans, I think, and then it realizes that there are no more loopless plans. So because, yeah, that there's a finite space of plans in this problem. So I think that's it from the hands-on. So I hope you didn't expect more, but I think like really it's like, at least I realized it, and I think you also, that people are really happy about having a Python framework, especially if they want to use it for their either in machine learning context, but also just for an application, right? Like you don't want to fiddle around with C++ and install it, but you want to download the package. And if you're just interested in getting plans and not how it works, I think that's a good option to do it.